All right, so yesterday we were talking about Newton's second law, okay? Newton's second law tells us, okay, that the relationship between the unbalanced or net force acting in a system is that it is the mass of the object multiplied by the acceleration of the object, or it is the vector sum of all involved forces. Okay, that's what we talked about. And we did an example with the people pushing the car there at the end of the day. Okay, so what we're going to look at today are a few more examples of that, and that's what we're going to spend quite a bit of time over the next little while looking at, is many different situations where that are governed by Newton's second law, how Newton's second law applies to them, how the forces work, okay, and things of that nature. All right, so we did one yesterday where all the forces were collinear. So what we're going to look at today is one where the forces are vectored. Okay, so they're not all in a line. What's that going to look like? All right, so let's just kind of imagine an example here. Let's say that I've got a big snowball. Some kids are making like a snowman. Okay, well, the two kids can't stand right side by side when they push on this ball. Okay, so one kid can stand like here, okay, and the other kid stands kind of here. I don't know why his hand is like that, but this is the way it drew. Okay, so I've got them both standing there. When this kid pushes on the ball, if I'm drawing this as kind of like a free body diagram, he's going to push like in this direction. And this kid's going to push kind of up, or maybe even a little bit angled, like over here a little bit. Okay, so those are the two forces acting on the snowball. Which way is the snowball going to go? How will I figure out where in between? Okay, I'm going to use some trig. Okay, this is a free body diagram. It's showing the forces acting from the center of the snowball. What kind of diagram will tell me what's actually going to happen to the snowball? A vector diagram. No, this is a free body diagram. A vector diagram. Okay, if I take these two forces and I draw them like I'm supposed to draw vectors, does that show the path that snowball is going to follow? Yes, it does. Okay, that's the direction the snowball will accelerate due to those two forces, because that is our net force. Okay, and we would calculate that in exactly the same way we did it in the last unit. We'd find x and y, and this would just have an x because it's horizontal, and we'd be able to calculate the net force. Okay, it doesn't really change anything. You can cry all you want, but vectors are still part of this. Okay, all right, that said, try this one. It's not a snowball, it's a block. But it's just like the snowball I just drew you. So give it a try. Okay, the two forces are force 1, okay, and it's force 1 is 35 newtons, 60 degrees from the horizontal, and force 2 is 10 newtons along the horizontal. So they've effectively already drawn you the free body diagram. Okay, they haven't done it the way I would do it. Okay, I would say that this is 15 kilograms. Okay, and I've got a 10 Newton force here, and I've got a 35 Newton, okay, 60 degrees from the horizontal. That would be my free body diagram. Now I need to find two things. The net force, and then I use the net force to get the acceleration. All right, remember yesterday we said every Newton's second law problem you do, you're going to have to find the vector sum of all forces and use m times a. Okay, not always in that order, but you're always going to have to do those two steps. All right, so I'm going to give you a little bit of time and see if you can get the net force with vectors and then get the acceleration from there. All right, so we've got our free body diagram there. Okay, if I want to find my net force, okay, and I need that because I'm trying to find acceleration, right? So the only way I can find acceleration is if I have F net and m. I have m, but I need F net, right? So I've got to find the vector sum of all forces in order to get F net. So that's going to mean taking this first force, which was 35 newtons, okay, and it was directed 60 degrees above the horizontal. So here's my X component and my Y component. Okay, and then I've got that 10 Newton force that was directed along the X axis, okay, like so. So my net force looks like this, except it's straighter. All right, so here's the Y component of it, the X component of it. So same as we've done in the past, okay, it's just now these are in newtons instead of meters. Okay, so I got to find black X. Okay, so black X will be the cos of 60 times 35, which would be 17.5 newtons. Okay, and then Y will be the sine of 60 times 35. I don't know what that one is off the top of my head. Okay, so sine of 60 times 35, all right, is 30.31 newtons. All right, so this one is positive. Well, we'll just say positive and positive for now. Okay, everyone all right with that? Okay, then obviously red X, okay, is 10 newtons, and red Y is 0. All right, so now that I have those, now I can find blue X and blue Y, same as I would have in the last unit. All right, so blue X is going to be 27.5 newtons, 17.5 plus 10, and then blue Y will be 10 newtons. So now I've got my, sorry, not 10 newtons, 30.31 newtons, sorry. All right, so now I've got those two sides of the triangle, so I can find the magnitude of my net force. Okay, it's 27.5 squared plus 30.31 squared. Not 28, 27 squared. Okay, so we're looking at 40.93 newtons. Okay, and then we'll find the direction, because obviously force is a vector quantity, so we'll have tan to the minus 1 of, for me, that'll be y over x, the way I drew it, so 30.31 divided by 27.5. Okay, is 47.78 degrees. All right, so now I've got my net force. Question doesn't want net force, question wants acceleration. So now I come back to this formula here. Okay, and I say that the acceleration will equal F net divided by m. Okay, so that'll be our 40.93 divided by 15 kilograms. All right, so we're looking at 2.7. I think we only have two significant figures here, right? Yeah, 35 only has two. Okay, so we're looking at 2.7 meters per second squared at 48 degrees above the x-axis, because that was the vector I was given in the question. Okay, everybody follow me there? Acceleration and net force always have the same vector. Why? That's where the object's going. One causes the other. Okay, the net force is the cause of the acceleration. I can't push something north and have it go east. Okay, they have to go the same direction. So net force's vector is always the same as acceleration's vector in these problems. Okay, questions on what we did there? All right, so really it's just what we did in the last unit with an extra step tacked on at the end with this F equals m times a stuff. No. Yes. Yeah, it's from this. Right. I just manipulated it for a. Yeah. Tim?
Did you also do like 42 degrees?
Oh yeah, absolutely. But because they gave it from the X, I just stuck with that. But yes, I could have said 42 degrees, right of the Y-axis or something like that, right of the positive Y-axis. Okay. Any other questions on that one? Okay. All right, so this is what we did, just typed out. Okay, it's essentially the same thing. All right, sometimes you'll get a question like that and it'll have a part B. So now they're saying, same situation, okay? When the force begins acting, the block is stationary. Determine the displacement of the block after 8 seconds. All right, so what do I know? I know VI. I know time. Right, and I know acceleration. Okay, can I find the displacement of the block? Okay, give you a minute. See if you can find it here. So this is just an acceleration problem, right? We don't even have to manipulate the formula. We're going to use d equals vi times t plus 1/2 at squared, okay? Which, since vi is 0, is just going to be 1/2 times 2.7 times 8 squared. So 0.5 times 2.7 times 64. All right, so we got 86.4 meters, but we only have 2 significant figures here. All right, so we'll be looking at 86 meters at 48 degrees above the x-axis. Why am I including that? Because it's displacement, and displacement's a vector quantity. Yes, because this would be part B. That's why I use the rounded value here too. Yeah. All right. Questions on that? I mean, you guys are good at acceleration problems, so that's pretty straightforward. All right, so we're going to look at a couple of examples. We'll start out pretty simple, and then we'll move to more complex stuff. Okay, we might even get to Newton's second law examples involving systems. Okay, systems mean there's more than one mass involved. One mass might be pulling on the other or something like that. Okay. All right, so we'll look at this one first. So we got a lacrosse player who exerts an average net horizontal force of 3 newtons forward on a 0.15 kilogram ball while attempting to pass it. Okay, calculate the average horizontal acceleration of the ball during the passing attempt. Okay, so here's what I know. There's only one force. Okay, they don't mention anything else. Okay, I don't need to worry about gravity or normal force or anything like that. It's just talking about the force of the net, okay, on the ball. And it's 3 newtons forward. Okay, I also know the mass, 0.15 kilograms. I'm trying to calculate the acceleration. How easy is that? Exactly. All I have to do is use this formula, okay? This is one of the ones where I didn't have to do vector sum of all forces because, yeah, they did it for me, okay? They said, here's the only force. Well, yeah, but it's because they said average net horizontal force, I knew this was the only force acting. So if there was another force, then I would have to do vectors and calculate it. Oh yeah, there's meters and seconds. Remember, what's a Newton? A kilogram meter per second squared, right? So yeah, I'm still going to get meters per second squared when I do this. So acceleration will be F net, okay, divided by m. So that's going to be 3.0 instead of newtons. I'll write kilogram, okay, meter per second squared divided by mass, which is 0.15 kilograms. So my kilograms cancel. That's what I was saying. Write newtons, but understand what a newton is so that you get the right units at the end here. Okay, so when we do that, we should get, was it 20? Yeah. 20 meters per second squared forward. Okay, it would be important to remember that that does require a vector, because acceleration is a vector quantity. All right, that's as absolutely easy as they get, because you didn't have to do the sum of all forces. Okay, they gave it to you. So don't expect to get too many more like that one. All right, try those two. Okay, the answers are here in brackets. Okay, I'll put them in blue here. So those are the answers. You'll know if you did them right. I'll give you a couple minutes on those. Okay, so let's look at this one as an example. So we got athletes in there, doing the, if you've ever watched, this is like one of the new Olympic sports, the kayaking, okay, where they have to go around the pylons that they put in the river, okay, these big poles, okay. So they're on a rowing team and they're training, okay. Athlete A has a mass of 65 kilograms. Athlete B, a mass of 70 kilograms. The canoe they're in, 20 kilograms. Okay. Athlete A can exert a rowing force of 400 newtons forward, and B, a force of 420 newtons forward. In the water, there's a resisting force, so water resistance, friction, okay, of 380 newtons. What's the acceleration of the canoe? All right, what's my first step in these always to draw? Okay, what kind of diagram? The free body diagram. All right, so inside the free body diagram is where I write what? The mass. Okay, what mass am I dealing with here? 20 plus 65 plus 70. It's not just the canoe. The two guys are in it too. All right, so we have to include all of them. All right, so we're going to have, we got 85 and 70 is 155 kilograms, right? All right, so 155 kilograms is the total mass being accelerated by the rowing forces. Okay, so we've got two rowing forces that are forwards. Okay, one that is 400 newtons and one that is 380 newtons. Oh, sorry, 420 newtons, sorry. And then our resisting force is 380 newtons. All right, so those are the three forces involved. Can I find the vector sum of all forces right now? Yes, and I don't need a vector diagram to do it. These are collinear. Okay, I've got 820 going forward, 380 going backwards, 560? Yeah, 440. Sorry, not 560. Yeah. Yeah. I don't know where that was coming from. See, that's why I shouldn't do math in my head. Okay, F net. Okay, vector sum of all forces, 400 plus 420 minus 380, 440 newtons forward. Okay, because forward was the direction we were given. All right, so there's our net force. Can I find the acceleration of the canoe now? Yes, so now I'm going to go net force also equals mass times acceleration. So acceleration equals F net divided by M. So that'll be 440, okay, divided by 155 kilograms. Okay, so 2.8, we only have two significant figures here. So 2.8 meters per second squared forward. All right, so we've done a few now, and they've all involved the same steps, right? At some point, I've got to find the vector sum of all forces. At some point, I've got to use F equals M times A, okay? Maybe I have to manipulate it, maybe I don't, but those two steps are always going to be involved at some point, okay, during one of these kinds of problems. All right, any other questions on that one? Okay. Try this one. Okay, read it carefully. There's extraneous information in this question that is there to distract you. So here's what we have. We have, notice I didn't record that part. I can't get in trouble. Okay, so we've got the mass, which is the bobsled, 225, okay, 323, okay, and 420, right? Is that right? Oh, I shouldn't do that in my head, but I did. Okay, so 420 kilograms is our total mass being accelerated. Okay, the force is acting on that. 1,200, 1,220, and 430. Okay, so there's all of our forces. Can I calculate the vector sum of all forces right now? Do I need a vector diagram for that? No. All right, so I've got 2,420, so we're looking at 1,990 newtons as our net force. Okay, so all we did was go 1,200 plus 1,220 minus 430, so 1,990 newtons forward, okay, is our net force. So now we can calculate the acceleration. It'll be our net force, 1,990 newtons, divided by our mass, 420 kilograms. That'll give us 4.7 meters per second squared forward. Okay, everybody all right with that? So sometimes it's not about the math. The math of this question was not difficult at all. Okay, it's the reading comprehension and making sure we get the right information and attack the question from the right angle. Okay, that can be kind of tricky sometimes. All right, elevator questions. Elevator questions are very, very common Newton's second law questions. Okay, like incredibly common. Now, when I say elevator questions, I don't just mean questions about literally elevators. Okay, I mean any object moving vertically due to forces is an elevator. Even this. Okay, just throwing something up in the air is an elevator question because I'm accelerating the object with my hand. I'm exerting a force on it. What force is acting against me? Gravity. Okay, anytime gravity and some other force are acting in opposition vertically, you have an elevator. Okay, if you're throwing a rock in the air, straight up in the air, you're pulling an elevator up, something like that, it's an elevator question. Okay, person jumps out of a plane with a parachute on. Okay, that's an elevator question, right? Anytime something's moving vertically with gravity involved, it's an elevator question. Now, here's the key. Anytime something is moving vertically, what force is involved? Gravity. You'd be surprised how often people will forget that, especially if I write it like this. Okay, a 2-kilogram rock is thrown vertically upward into the air with a force of 200 newtons. Calculate its acceleration. You would be surprised how often people will take gravity completely out of that, and they'll just go 200 divided by 2. Okay, they'll just totally space on the fact that I threw something straight up in the air and gravity should be involved. Okay, so always remember, moving vertically, gravity's involved. Go. Well, if it's diagonal, then gravity is a component force. Yeah, there would be then vector addition stuff. These are elevator questions are literally vertical. All right. So for this example here, make sure you write this one down because we're going to go through it here. Okay. I have a person and an elevator with a combined mass of 600 kilograms. So they've kind of drawn a free body diagram here. I would just add that this is 600 kilograms. Okay. The elevator cable exerts a force of 6.5 times 10 to the 3 newtons up. Right. So again, I usually write those numbers on there. Okay. 6,500 newtons. That's the tension in the cable. Okay. The lifting force of the cable. And then I've got the force of gravity acting down. How do I calculate that? I showed it to you yesterday when we were talking about weight. Oh yeah. Now I remember you showing me, but I don't remember what you showed me. Okay, here's how we do it. Force of gravity equals mass times the acceleration due to gravity. Okay, it's Newton's second law, but it can also be applied to individual forces. Any individual force is mass times the acceleration that force can produce. Okay, so in this case, we've got mass times gravity. So that'll be 600 kilograms times 9.81. All right, so we're looking at 5,886 newtons. All right, they don't mention anything about friction or air resistance, so we'll assume that those are not applicable here. Okay, those are our only two forces. 6,500 newtons up, 5,886 newtons down. Which way is the elevator going to accelerate? Up. Okay. Can I find out how much? Yes. All right. First thing I want to do, I got to find F net because I need F net when I do mass times acceleration. So it'll be the vector sum of all forces, 6,500 minus 5,886. All right, so we're looking at 614 newtons, right? All right, and that's up. All right, now I can use F net equals m times a and calculate the acceleration. So that'll be 614 divided by 600. Okay, so we're looking at 1.02, because we do have three significant figures here, 1.02 meters per second squared. Up. All right. So our elevator question is very hard. No. Here's the thing. Sometimes an elevator question will say, here's the acceleration of the elevator. Find the tension in the cable. So you'll work backwards. Okay. You have the acceleration, you have the mass, so you find the net force. Since you know the mass of the elevator, you can find the force of gravity acting on the elevator, and then you'd be looking for this instead. Okay, not really any more difficult, it's just a different order. Okay, but we still use sum of all forces and m times a. Okay, everybody all right with that? Okay, so very, very typical question. Okay, it's almost always one of those on a quiz or an assignment or something like that. Okay, elevator questions are very, very common. Anyone need that one anymore? All right, so now question number one is dealing with the same person, same elevator. So I'll remind you that the mass of that elevator was 600 kilograms. Okay. Now the cable exerts only 5,200 newtons worth of force. Find the acceleration of the person. Okay. And then after that, try number two. But I'll tell you that number two is tricky because I haven't taught you how to do it yet. Let's see how many of you figure it out. Question number two. Okay. Question number two gives you very different information than any problem we've done thus far. Okay. It tells us that this electric chain hoist in a garage can exert this much force upwards. Okay, so that's nice. I mean, we know how much force is going up. Okay, and we know that it's 2.85 times 10 to the 3 newtons. So 2,850. We'll just write it like that. Okay, on an engine to remove it from the car, the acceleration of the engine is 1.5 meters per second squared up. Okay, what's the mass of the engine? Okay, so this is a bit troublesome because they don't give me the mass of the engine. I have to find it, and that makes things difficult because that's been part of everything we've done. F equals m times a. Everyone okay with that? All right, but here's the thing. All forces, okay, like we said, F net equals m times a, but in the last question, we also found that Fg equals m times g. And I said to you, any individual force can be calculated by taking the mass being accelerated and multiplying it by the acceleration the force can produce. That's why the force of gravity is calculated by going mass times 9.81. Any individual force can be calculated by going mass times whatever the acceleration that force would produce alone would be. Okay. So for right now, I know I've got 2,850 newtons, okay, going upwards, right? So if I do F net, okay, that's supposed to be the vector sum of all forces. So that means the force of the hoist plus the force of gravity, which would be a negative number. Everybody okay with that? All right. These forces can be calculated by doing this. Mass times acceleration, net, okay, equals mass times the acceleration of the hoist plus mass times acceleration due to gravity. What do all three of those terms have in common? Mass. Okay, now this is going to seem counterintuitive because I'm looking for mass. What can I do with mass? Right, I can cancel it. Okay, if the net force is the vector sum of all forces, it's also true that the net acceleration is the vector sum of all the accelerations. Okay, everybody follow me there? Okay, because we said mass is the same for all of these, so I can just say this. All right, now you're probably looking at it and going, how the hell does that help you? You're looking for mass. You don't have this number, but do I have this one? It tells me the engine is accelerating at 1.5 meters per second squared up. Do I know this number? Yeah, it's 9.81. Can I calculate this number? Okay, how's that going to help me? The force of the hoist is the mass of the engine, which I'm looking for, times the acceleration of the hoist. And now I've got a way to find the acceleration of the hoist. Okay, we call this the differential acceleration method. Sounds really complex, but really it's just the net acceleration. Okay, net force and net acceleration work the same way. All right, so here's what I'm going to do. I'm going to solve for the acceleration that the hoist could produce alone. And that's going to mean I take the net acceleration and I subtract g. So that's going to be 1.50, okay, minus negative 9.81. Everybody all right with that? Okay, so when I do that, okay. All right, so if I only had the hoist and it didn't have to work against gravity, it would throw the engine vertically upwards at 11.31 meters per second squared. Okay, and that should make sense. The only way for the engine to move upwards is for the hoist to pull harder than gravity. Okay, so now I know the acceleration of the hoist. And now I can say the force of the hoist, which I know because they told it to me, is equal to the mass times the acceleration of the hoist. And now I have this number and this number. Okay, so I can solve for the mass of the engine. These questions don't come up very often, okay, but they come up once in a while, so it's important to understand how to solve them. Okay, so we're going to have 2,850 divided by 11.31. Okay, so the mass of the engine is 252 kilograms, okay, which is pretty heavy. That's over 500 pounds. Yeah, it's heavy. Yeah, well, or even a kind of a, yeah, massive V8 that's, steel and not aluminum. Okay, modern engines are a bit lighter because they're made of lighter weight alloys, but okay, if you were pulling a big block out of an old car, it would be heavy. Yeah, with the transmission still attached, yeah, it'd be really heavy. Okay, that's why you need one of those. So if you've ever watched like Fast and Furious, any of those movies, there's a scene where Vin Diesel grabs the chain from one of these hoists and is like holding the engine with one of his massive arms. Looks really cool, but no way. There's no way. Yeah, yeah, something like that. I don't remember which. They all blend together because they're all the same. All right, so that one makes sense? Okay, so differential acceleration doesn't come up very often, but once in a while it comes up. So we need to understand that any force, and this is what we're supposed to get out of this, any force can be calculated by taking the force it produces and multiplying it by, the mass being accelerated and multiplying it by the acceleration that force can produce alone. Okay, so that's true for all individual forces. Okay, so case in point, differential acceleration method question. All right, give it a try. Skydiver jumps out of a plane. So it's an elevator, just like the hoist question was, but it's also a differential acceleration question. All right, so I'll give you a few minutes on that one. All right, so the skydiver jumps out of the airplane. During the first few seconds of one jump with the parachute unopened, the magnitude of air resistance acting on the skydiver is 250 newtons. So if I'm looking at a Freebody diagram here, okay, I don't know the mass of the skydiver, but I do know that the upward force on them is 250 newtons. Okay, and we know that the acceleration of the skydiver, okay, his overall acceleration or his net acceleration is 5.60 meters per second squared, and that's going to be negative because it's downwards. Okay. calculate the mass of the skydiver. All right, so the other force that's acting here is gravity. I can't calculate the force of gravity because I don't know the mass of the skydiver. What I do know is 2 out of the 3 accelerations. So I'm going to go back to this and say the net acceleration is equal to the acceleration due to friction, so that air resistance number here, okay, plus the acceleration due to gravity. Since I have those two numbers, I can calculate the acceleration that would be produced by this force. Everybody okay with that? All right, so that's what I'm going to do. The acceleration due to air resistance is going to equal our net acceleration minus g. So that's going to be negative 5.6 minus negative 9.81. That'll give me a positive number, and it should be positive because it's upwards. Whoop, 9.81. All right, so the acceleration due to air resistance is 4.21 meters per second squared. Up. Now that I know that, I can plug it in here and solve for the mass of the skydiver. Okay, so we'll take the force of friction is equal to the mass times the acceleration due to friction and solve for mass. So mass will be 250 divided by 4.21. So my skydiver has a mass of 59 kilograms. Sorry, did I say wrong? Sorry, 5.96. I don't know, because I said it was 5.6 and I'm wrong. So let's try that again. Next time, can you tell me I screwed up before I get finished? Save me some time. And I wrote it right underneath the other number too. God, some dates. I haven't drank all my coffee yet. That's going to be it. Okay, so 5.96 minus negative 9.81. Oh, I wish. All right, 3.85. That better? Meters per second squared. Okay, so then we'll do 3.85 here. $65 kilograms of mass of the skydiver. Okay. All right, everybody okay with that one? Now that I did it right, use the right numbers. Okay. All right, I want you guys to try just number 1 for right now. Okay, I'll make it a little bigger so you can read it better. So the bungee jumper, okay, is the square, 55 kilograms. Okay, so she's tied by her ankles, okay, and she jumps off the bridge. So we've got the force of gravity acting downwards, which we can calculate, m times g, and we have the force in the elastic, which we were told is 825 newtons. All right, so we just need to calculate this force here. So 55 times 9.81, right? And we've got the two forces that are acting. So we got 539.55 acting down. We've got 825 acting up. Can I find the net force on her? Okay, so F net, okay, will be 825 plus negative 539.55, okay, giving us our net force here. So 825 minus our answer. All right, so our net force is 285.45 newtons. If I want to calculate her acceleration, okay, then I plug that into A equals F net over M. Okay, so I just divide that by 55. All right, so her acceleration is 5.19 meters per second squared up due to the bungee cord, which is what you want when the ground is rushing towards you, okay, after you jump off the bridge. Okay. All right, questions on that? All right, so we'll be working a bit more on that tomorrow, looking at some more complex situations tomorrow, maybe even moving into systems tomorrow. Okay.